Okay, so where we left off in the previous video is we walked through how to draw up the shorthand for a cell, how to think about different components of a cell, how to break apart a cell into its half reaction components, and then how to use those half reaction components and their corresponding standard reduction potentials to compute the direction in which the overall redox reaction is going to be spontaneous. And the conclusion we came to is that every half reaction or every full cell reaction will be spontaneous in one direction and non-spontaneous in the other. And in terms of echem or electrochemical terminology, we mean in every full cell reaction will be galvanic in one direction and electrolytic in the other. And where we left off, though, was this hanging punchline that said actually the cell that we'd created, even though it's spontaneous, it's not going to pass current through an external body. And the reason for that is because we just mixed everything together in one pot. And of course, if you do that, there's nothing stopping it from just simply reacting in the solution itself. And so we have to be clever with our design of an electrochemical cell so that we can decouple the electrons from the chemical reactions. In other words, we need to separate the two half reactions physically in space such that the electrons via a reduction or oxidation actually have to travel through an external body in order to go to the place they need to go to affect the oxidation or reduction. And so we have exactly the same cell that we had in the previous video, but now we've physically separated or isolated the two half reactions in two separate vessels. And so we have the cadmium and the cadmium 2 plus half cell on the left, and we have the silver 0 and silver plus half cell on the right. The exact same two half reactions are at play here. The overall cell potential is still 1.2 volts for this cell. Our shorthand, you can see I have written up here. We still have the oxidation step and the reduction step, so the two half cells are exactly the same, at least in the spontaneous direction. The only thing that changes here, and this may be hard to see, but you've got this sort of double vertical line here that we didn't have before. Remember, in the previous version of the cell, the one that just reacted in the beaker and did not have an externally routed current, we had a comma here instead, and the comma just meant that we had both salts in the same solution. Everything was just dipped in the same solution. The two vertical lines here refer to this thing, which is the salt bridge. So the salt bridge is simply a means to connect the two cells together, but to keep them physically isolated but electrically in contact. And so as long as you have that there, you can imagine this whole thing as a circuit, which it is. You have electrons that are moving in this direction, and they're moving through the circuit into the silver electrode, through the silver electrode, and then they reduce the silver ion and convert that to silver 0. So in that case, we've destroyed some positive ion in the solution, so this thing is becoming less positive. And so what happens then is the solution will just halt at this point. If we had just our half cells completely separate but no salt bridge here, then the second we reduced one silver ion to silver atom, we now have destroyed electroneutrality. This solution is no longer electroneutral. And so what the salt bridge allows us to do is the salt bridge is this tube, usually a U-tube like this, that's packed with either gel or just a concentrated solution of an inert salt, in this case potassium and nitrate. So what happens is when you take the silver plus and you tack an electron on and you destroy it and you make silver 0, you have just made this solution less positive because you just destroyed that positive and you turned it into a neutral. And so what the salt bridge does then is it takes some of that potassium ion that's saturated in the salt bridge where there's tons of it, and that just slowly diffuses to then give you a positive charge. So every time a silver ion gets destroyed, a potassium ion diffuses into the solution. If we look at the other side here, where we have cadmium now dissolving and forming cadmium 2 plus, this solution is becoming more positive or less negative, in which case if this is becoming less negative, then every time this reaction runs once, or that half reaction cycles once, and we create a 2 plus, we get 2 of these nitrates that then diffuse into the solution to counterbalance that and preserve neutrality in the system. So the salt bridge is really operating in two different ways. One is it's preserving the electrical circuit. It's connecting this circuit, but what it really means to connect the circuit here and run this contiguously through the system is because electrons aren't being transferred through the system, but electrons are being transferred out here. That means where electrons are being shuttled into this side, and that means that that negative charge then, instead of electrons, we have nitrates, gets shuttled this way. And that keeps the electroneutrality preserved in this case. Just to iterate here, the salt bridge is the double vertical line. Everything else is the same. The single vertical lines denote the phase change, and I just wrote an energy diagram here at the bottom just to be clear what's happening here. You've got cadmium 0 here, that's the metal. That's at a higher energy state because it's in a negative, it's minus 0.4, and as always their voltage, it's higher energy at more negative voltages, which is in this top upward going direction. That thing's full of electrons because it's cadmium 0, and those electrons are going to cascade down to a lower energy state, which is to fill up and pump up these silver pluses and drive the reaction forward. And the net difference between those half reactions from high energy to low energy is that 1.2 volts, which is our cell potential. And so it's no mystery here that if we then wanted to run this reaction in reverse, then we're taking electrons that are down in this state and we're trying to get them up to this state, which means we're going to have to put 1.2 volts of energy into the system rather than gaining 1.2 volts. And in that case, then we'd be applying a minus 1.2 volt voltage to the system to get this to run.